Hello class, this is Ms. Riggins with today's video on section 3.6, the chain rule and inverse functions. As you're watching the video, please remember to take down any important information, notes, formulas, equations of the like, as well as feel free to pause, rewind, or even replay the video as often as you need to. At the end of watching the video, write your online summary in your notes as well as submit it online as well as the top question. All right, let's begin. Today we're going to be talking about using things that we've already been experiencing or using in the past, but using them together, which is using the chain rule and inverse functions. And to be more specific, we're going to use the chain rule to differentiate inverse functions. And so let's take a look at the derivative of a power function y equals x. Now, of course, we all know what that is, to find the derivative of that, for n being a positive integer, and we've used it when it's not a power function, when n is not a positive integer, if it's a positive number but not an integer. But let's actually go through the proof, or not the proof, but showing you that dy dx is really n times x to the n minus 1, whether or not n is a positive integer or whether it's just a positive number, or it doesn't even have to be an integer at all. So what we're going to do is we're going to take a look at two different derivatives and see how they relate. So let's take a look at the first derivative, which is natural log of x. So very quickly, e to the natural log of x is equal to x, and that's just using inverse properties. So if I want to take the derivative of both sides, I get the derivative of both sides are equal to each other. Well, the derivative of e to the natural log of x, because this is exponential, is the same function times the derivative of the exponent. That's using chain rule right here. And then the derivative of x is just 1. So we end up with this statement. And if we solve for or isolate derivative of dx, if we isolate that, then we end up with derivative of natural log of x is equal to 1 over e over to the natural log of x, which we know because of inverse properties is equal to 1 over x. So a very, very important derivative formula is that the derivative of natural log of x is equal to 1 over x. Okay, let's take a look at the other situation, which is a to the x. Okay, so using the same property, using the relationship. Now, if you recall, the natural log of a to the x is equal to the natural log of a times x. Okay. And that's just a property of logs, is that when you raise this to the exponent, you bring this exponent down, and it's the same thing. So then I take the derivative of both sides, and as we can see, the derivative of this side, we're going to use the rule we just found out is the natural log. We use the result that we just found over here, which is derivative of natural log of x is equal to 1 over x. And so since we're taking the derivative of a up to the x, then that's equal to 1 over a to the x times, using the chain rule, derivative of whatever a to the x is. Well, we know that the derivative of a to the x is equal to the natural log of times a to the x. And when we divide that by 1 over a to the x, we just get to the natural log of a. There's a step that we missed algebraically, but I just explained it verbally. Okay, so that's another way to prove that the derivative of the natural log of a to the x is equal to the natural log of a. Okay, using this property. Sorry, I'm all discombobulated. All right, let's move on. So let's actually apply this idea to find the derivative of inverse trig functions. So if you remember, the tangent of arctan, if you guys aren't familiar with the terminology arctan, it's really the same thing as tan inverse. So the tan of arctan of x is equal to x, and that's just inverse properties. So let's take the derivative of both sides. And we take the derivative of both sides, then I know that this right side is going to be 1. But using the chain rule, I know that the derivative is found by taking the derivative of tangent, which is cosine squared, and multiplying it times the derivative of the inside. Okay? I think I missed writing something down here. Oh, yeah, I missed something writing down. Let me fix that quick second. Okay, so I fixed that. This I have forgotten to type in the tan. So anyway, the derivative of this statement is using the chain rule is the derivative of tangent, which we know is 1 over cosine squared of the inside, times the derivative of the inside, which we know is the derivative of arctangent of x. Well, since we don't know what the derivative of arctangent of x, let's go ahead and try and isolate that by multiplying both sides by cosine squared arctangent of x. And when we do that, we end up isolating derivative of arctan x to be equal to cosine squared arctangent x. Okay? And then using the identity that 1 plus tangent squared of theta is equal to 1 over cosine squared theta. Well, actually, you might remember the identity as 1 plus tangent squared theta equals secant squared theta. But, of course, secant squared theta is the same thing as 1 plus cosine squared. So that must mean that we can apply this to the derivative of the arctangent, which we said was already equal to cosine squared arctangent of x, to be equal to